Find the domain of the following functions. In this problem, we will be looking at 6 different examples relatively quickly. Let's start. In part A, f of x equals 3x minus 4. This is a linear function, and the domain of any linear function is negative infinity to infinity. Part B, the function g of x equals 7x squared plus 2x minus 6. This is a quadratic function. This gives the graph of a parabola. It turns out this domain is also negative infinity to infinity. Okay, part C. We have the function h of x equals 2x minus 6 over x minus 5. The first example where the domain is not all real numbers. Here, since there is an x in the denominator, that means there could potentially be a divide by zero situation. In order to figure out where that is, we're simply just going to set the denominator equal to 0 and solve for x. That tells us x equals 5. So as long as we pick any other number other than 5, this function will exist. So that's exactly what the domain is, where the function exists. So the function can exist all the way from negative infinity to 5, but we cannot include 5. Now this is everything happening to the left of 5. This function also exists to the right of 5 as well, but we still cannot include it. But we do know that it will go all the way over to positive infinity. So this is the domain for part C. Part D and E are going to be very similar. So when you're working with a square root function, what you need to do, or what we like to have for square roots that have real resulted answers, that means the inside of the square root needs to be bigger than or equal to 0, because those are the numbers that we can actually type into a calculator and get back some either whole number or decimal approximation. So we need to take just what's on the inside of the square root and set it to be bigger than or equal to 0. When you solve for x, that means x is going to be bigger than or equal to negative 8. And then in interval notation, that means negative 8 off to infinity. And we include it because of the equal to. So there's the domain for part D. Part E, it's very similar. We're just going to take the inside, set it to be bigger than or equal to 0, subtract 9 from both sides, negative 3x is greater than or equal to negative 9. Divide both sides by negative 3, that tells you x is now less than or equal to 3. And this inequality sign switched directions because you're dividing by a negative 3 in this inequality. So this is the domain, but in interval notation, this looks like negative infinity to 3, and you include the 3. There is your domain for part E. And part F, this is an exponential function, and there are no restrictions here, so we can just jump right ahead to the domain of negative infinity to infinity. The last type of function that has domain restrictions is the log function. So you'll want to make sure that if you're trying to find the domain of a log, that you set insides just to be bigger than 0 and solve for x, or solve for whatever variable happens to be there. So there were 3 functions that had domains that were not all real numbers. The first one we looked at was the rational function. The next type we looked at was the square root function. Notice these domains are not all real numbers. And the last one that there was not an example of is the log function. It's very similar to finding the domains for these square root functions, but you set the insides to be bigger than 0, not bigger than or equal to 0. Let f of x and g of x be defined below. Here they are. F of x is 2x plus 5, and g of x is x minus 4. We will be working with function operations in these 2 examples. In the first example over here, we're trying to find f plus g of 3. And what that means is that we want to find f of 3 and then add to that g of 3. So we're adding 2 functions together here, and we want to evaluate that at 3 is the same thing as saying find each function individually evaluated at 3. So here, f of 3, if we come up here and substitute 3 in for this x and this x, ends up being 2 times 3 plus 5. So that is all this right here. G of 3 is what you get when you put 3 in for x here and here. So when you do that, you'll get plus, I should put this in parentheses, plus in parentheses 3 minus 4. So g of 3 is all of this here. From there, you can just crunch some numbers. This first part here is 11. This second part here is negative 1. 11 plus a negative 1 is 10. So there's your answer for the first example. In the second example, over here we have f minus g of x. So we aren't even trying to evaluate the functions at any specific x value. We're just going to essentially combine like terms. This will be f of x minus g of x. So all we have to do is substitute whatever f of x is equal to. It's 2x plus 5. So this will be 2x plus 5, and I'm going to put that in parentheses, minus g of x. G of x is up here, and that is equal to x minus 4. So over here in parentheses, I'll have x minus 4. My next step would be to distribute this negative to both terms there, and you'll get 2x plus 5 minus x plus 4. And when you combine all of these terms here, you will get x plus 9. So there's your answer for the second part. Let f of x and g of x be defined below. F of x is defined as equaling x squared plus 2x minus 4. G of x is defined as equaling 3x plus 2. Our goal here is to find f of g of x, or f compose g of x, and g compose f of x. So how we can do this, how we can think of this, is this composition means you just put one function inside of another function. So this will look like f compose g of x, or sorry, f of g of x. The next step is to substitute in whatever g of x is equal to. Essentially, this 3x plus 2 will replace this g of x, because after all, g of x is equal to that. Oops. So I will write f of 3x plus 2. So what does that tell you to do with this 3x plus 2? Well, normally we'll write f of x, but that x here got replaced with 3x plus 2. So that means all of these x's over here will also get replaced with this 3x plus 2. So over here I'm going to write, we need to have x, but it's not x anymore, it's 3x plus 2 squared plus 2 times 3x plus 2 minus 4. The next step is to simplify all of this. You can FOIL that out. You can distribute the 2 to both of the terms inside. And when you do that, you'll see that you get something like this. And now all we have to do is combine like terms. So here I have some x squareds. In red underline I have some 6x's, and in the blue underline I have constants. So when you combine all of these together, you will get this. And this will be your final answer for your composition. In this next example over here on the right, g compose f of x, we're going to do something very similar. We're going to rewrite this like we did with this f compose g of x. So what this will be is this will be g of f of x. So that will be equal to that. There we go. From here, we want to replace f of x with what it's equal to. F of x is equal to x squared plus 2x minus 4, so I'm going to replace this f of x with x squared plus 2x minus 4. So g of x squared plus 2x minus 4. From here, we now have g of some giant looking function. Normally there's just an x there. So x got replaced with all of this. That means up here in the function, this x will also get replaced with all of this. So this function equals 3 times x squared plus 2x minus 4 minus 2. Now to simplify, you just have to distribute this 3 to all three terms on the inside, and you will get this for your final answer. Now I went ahead and distributed the 3 to the negative 4 and got negative 12, and subtracted 2 more right away. So this is your answer for the composition g compose f of x with these two functions.